Dr.S.Amala, lecturer in chemistry, Sita Ramaswamy College, Tiruchirappalli. I am going to discuss about defects in crystals. An ideal crystal defined as the same unit cell containing the same lattice points throughout the whole crystal. At absolute zero, most of the ionic crystals contain well-ordered arrangement of constituent ions. Hence, there is no imperfections or defects. But with the rise of temperature, one or more lattice points become unoccupied or vacant, leads to defects in the regular arrangement of constituent ions of the crystal. On the basis of the above discussion, we have concluded that there are two types of defects are arised. One is stoichiometric defects, another one is non-stoichiometric defects. Stoichiometric compounds are those in which the ratio of the number of cations to the number of anions is equal to 1. That is, the number of cations is equal to number of anions. These defects are further classified into two types. One is Schottky defect, another one is Frenkel defect. Schottky defect arises when some cations and equal number of anions are missing from their own position and thus leave lattice vacancies or holes in the crystal lattice. Since the number of missing cations is equal to the number of missing anions, the crystal as a whole remains neutral. In this defect, the missing cations and missing anions leave their original position and move to the surface. This defect is mostly found in compounds which have high coordination numbers and compounds in which ions are almost of the same size. The alkali metal halides like sodium chloride and cesium chloride have Schottky defect. This picture represents the Schottky defect produced by missing of one anion and one cation. This is the cation missing hole and this one is the anion missing site. Frenkel defect arises when one of the ions leaves its own position and occupies interstitial positions in the lattice. Cations are being smaller in size, therefore more likely leave their position and enter into the interstitial position in the lattice. Since the number of cations is equal to the number of anion, the crystal as a whole remains neutral. In this effect, the cations move to another position between the two layers. Therefore, the cations surrounded by greater number of anions. This defect is mostly found in compounds which have low coordination number and compounds in which the negative ions are much larger in size than the positive ions, and compounds which have high polarizing cation and an easily polarizable anion. The zinc sulfide and silver bromide possess Frenkel defect. This picture indicates the Frenkel defect produced by the movement of one cation and occupying the interstitial position in the lattice. These are all the consequences of Schottky and Frenkel defects. As already we have seen that in Frenkel defect, similar charges come closer to each other. This closeness increases the dielectric constant of the crystal. As we know that in Schottky defect, the number of ions in the lattice of the crystal is decreased. This leads to the decreases the density of the ionic solids. The presence of holes in Schottky and Frenkel defects lowers the lattice energy of the crystal. As a result of both types of defects, the crystal is able to conduct electric current, in which a hole migrates from one end to other end and conduct the electricity in the whole of the crystal. Let us discuss about the non-stoichiometric defects. Non-stoichiometric compounds are those in which there is a departure from stoichiometry based on the law of constant proportions. The excess of either positive ions or negative ions in the non-stoichiometric crystals makes the crystal structure irregular. These non-stoichiometric defects may exist in a crystal in addition to Schottky and Frenkel defects. Non-stoichiometric defects also may be of two types. One is metal excess defect Another one is non-metal excess or metal deficiency defect. First we have discussed the metal excess defects. This metal excess defect is produced due to the presence of excess of positive ions in the crystal lattice. This excess of positive ions can be of two ways. In the first way, one of the negative ion is missing from its real position, leaving a hole, and hole is occupying an extra electron due to the maintenance of neutral nature of the crystal. The negative ion leaves the surface in the form of gas. For example, when excess of sodium is burnt in chloride, we get a yellow color sodium chloride. This yellow color is due to the electrons occupying the position vacated by the missing anions. This center is called F centers. Defect, these metal excess defects is found in those crystals which have Schottky defects. Here note that in this metal excess defect, there is a one hole that is also occupied by extra electron. But in Schottky defects, there is two holes. In the second way, an extra positive ion occupies a position in the lattice, and in order to maintain the electrical neutrality of the crystal, an electron is also occupies the interstitial position in the lattice. This metal excess defect is found in those crystals which have Frenkel defects. Here note that this metal excess defect has no holes, but the Frenkel defect has only one hole in the lattice. This picture represents the metal excess defect due to the anion vacancy. In that anion vacancy site, in order to maintain the electrical neutrality, electrons occupies the anion vacancy site. This is the metal excess defect due to the presence of interstitial cation. In the defect also, in order to maintain the electrical neutrality, electron is also occupies the interstitial position. In consequences of metal excess defects, the crystals conduct electricity to some extent with the help of these free electrons. Since the number of free electrons is very small, they can conduct electricity only to a small extent. So that the crystals having metal excess defects are called semiconductors. Next consequences is due to the presence of free electrons, the crystals having metal excess defects are generally colored. Reason that the free electrons are easily excited to higher energy state by the absorption of wavelength in the visible region. That's why the compounds are colored. Example, the non-stoichiometric sodium chloride is yellow, and zinc oxide, which is white in cold but appears yellow when hot. Non-metal excess defect or metal deficiency defects are produced by the presence of excess of negative ions in the crystal lattice. The excess of negative ions can be achieved by any of the following methods. In the first way, one of the positive ion is missing from its position, and one of the adjacent cations acquires one extra positive charge on it and becoming A2+ in order to maintain the electrical neutrality of the crystal. Such a cation should be of transition metals because they possess variable valency. In the second way, an extra negative ion occupies a position in the lattice, and one of the adjacent cations acquires an extra positive charge on it in order to maintain the electrical neutrality of the complex. Here we noted that usually the anions are bigger in size, therefore very difficult to occupy the interstitial position. Therefore, there is no crystals containing extra anions occupying the interstitial positions in the lattice are known, and hence the metal deficiency defect represents only a theoretical prediction. These two pictures represent metal deficiency defects. The first one is the metal deficiency due to cation vacancy. This is the cation vacancy site. The adjacent cation becomes A2+ in order to maintain the electrical neutrality of the compounds. Second one is the metal deficiency due to an extra anion occupying interstitial site. In that defect also, the adjacent cation becomes A2+. As a consequences of metal deficiency defect, one of the cation A plus is changed into A2 plus cation. This type of conversions takes place through the movement of electron from A plus to A2 plus. This type of movement is called movement of the positive pole, makes the crystal with the metal deficiency defects act as semiconductors. Thank you.